So we should probably ask why it might get tricky to design a really good evaluation function. Well, just to give a little hint here, let's imagine that we do start with the idea that we could take the difference in material value between blacks and whites pieces in a chess game. That would lead to the idea where the evaluation of a position is calculated by looking at which pieces black still has on the board, looking at which pieces white still has on the board, in each case adding up the material value, and then looking at the difference. Well, an immediate problem with this is that from the start of the game, every position you look at is going to have the same evaluation, namely 0, up as far as the point where a capture is first made. Every position in the game, until you get a capture by one side or the other, is going to have the same evaluation, namely 0, because at the start of the game each side has the same pieces. And in a similar way, all the positions where, for example, one player is a single pawn ahead of the other are going to evaluate in the same way, even though a chess player will tell you that some positions, even before a capture has happened, may look an awful lot stronger than others. So we would need something considerably more subtle than just the difference in material values. Now, we're not expert chess players. Well, some of you might be, but I'm not. So I'm not going to go into great detail in terms of how one might design an evaluation function for a particular game. I'll just point out that one way in which people have tried to do this has involved introducing machine learning into the process. Now, as a starting point, we could, for example, try and evaluate a position by taking a weighted sum, the weights here are the Wi, of features Fi of the position. Now, those features could, of course, just be material value for the individual pieces, and we could try and learn these weights W in order to get some kind of better evaluation function. And by learning here, I mean just adjusting those weights to try and find values that lead to an effective evaluation function. And we might, for example, do that by allowing the game AI to play itself and thereby explore which weights led to a stronger player. That, of course, would still leave us in a position where all game positions with the same pieces would have the same evaluation. So you might want to introduce more interesting features. For example, a Boolean feature that tells you whether or not one player's queen is being attacked, or the number of attacks that are currently being made on one player's king, or some measure of how well a player is occupying the centre of the board. And a chess player would come up with all manner of different things that you might try and measure that would make good features here. Now, there's one further thing to add here, of course, which is that in the examples I've given so far, I'm generating the tree from the starting position of the game. But of course, we can take any position and we can specify whose turn it is to move, and we can then use that as the root node in producing a game tree. So in fact, the way we might want this to work would be we'd start with the current position within the game and an indication of whose turn it is to play. Then we would generate all possible moves the player can make from that position, and so on, producing the tree as far as it takes for the cutoff test to come into play, at which point we stop generating the tree and evaluate the leaf nodes with the evaluation function. We can then apply Minimax to those leaf nodes with the evaluation functions, come back to where we started, which is some point within the game, and that gives us a way of assessing which move to make, because the move at that point that we've established is the one that our player makes if playing rationally, is the one that we pick. So what have we got so far? Well, we can in principle make the whole game tree, but we can't do it in practice. So we want to introduce a cutoff test and an evaluation function. Now, in the case of chess, even that isn't really going to give you the ability to make any kind of particularly strong player. The search process for generating the partially completed game by generating the game tree as far out as the cutoff test will let us, and then labeling each of the leaves that we've got after applying the cutoff test with the evaluation function, and then applying Minimax to that, well, we're still going to end up with a sufficiently complex game tree that just the process of doing Minimax isn't going to give us a very effective player. But we can go one step further and introduce the idea of alpha-beta pruning. And the idea here is to try and avoid doing Minimax over the entire search tree. And the way in which we do that is to try and make a decision while we're doing the Minimax process. Okay, the process of starting at the leaves and backing up values depending on whose turn it is to play, in order to back up all the way to the root, which will be one of the players in the position that they're making a move from. So to summarise, what we initially said was that we could, in principle, start at the beginning of a game, generate the entire game tree, label the leaves of the game tree according to whether there was a win or loss or draw for one of the players, then back up from the leaves towards the root, at each stage taking a maximum or minimum of the child values for a given node, depending on whose turn it is to play, and by doing that all the way to the root, we get an assessment of which opening move to make. I then suggested that because we can't do this for the entire game tree, we should have a cutoff test which allows us to stop expanding the tree out at some point before the game is finished, and we should have an evaluation function which allows us to label a leaf representing an incomplete game according to how good it is from the point of view of one of the players. And then finally, rather than generating this tree from the beginning of the game, we can at any point generate it starting at the current game position, go out as far as the cutoff will let us, label leaves with the evaluation function, and back up as far as the current position in the game in order to decide what to do next. Now, the idea with alpha-beta pruning is that because this is still too complex to deal with for any kind of interesting real game, we want to try and avoid parts of this process if possible. So while we're producing the game tree out as far as the cutoff from our current position, we want to try and establish at each point if we can avoid generating bits of the tree, but we also want to do this in such a way that we never miss any of the possibilities. And this is what alpha-beta pruning allows us to do. So I'm going to return to the earlier example initially, because this makes it particularly straightforward to show how this process might be possible. Here I have the simplified game tree that I used as an example earlier on. And we're going to do this minimaxing process in a depth-first way, moving from left to right, in the time-honoured fashion. So what's going to happen? Well, what happens is we go depth first, left to right. We go down the left-hand side of this tree in the diagram. And at that point, when we're at the leaves, we know that the outcomes that we've got are the outcomes that can be achieved by Min, if she plays them. So those are 4, 5, 2 and 20. So in our left to right depth first manner, we see the 4 and the 5 and the 2 and the 20, and we keep the smallest. Then we back up the tree. When we back up the tree, we take the smallest that we've found in the 4 children, and we label the node using that. So the node gets labelled as a 2. Then we come back to the root. we go depth first down the second subtree, we repeat the process. We go through the 20, the 15, the 6 and the 7. We keep track of the smallest, which is a 6. And as we back up, that's the value that we assign to the min node in the second subtree. Now the interesting thing is what happens at the next part of that process. So now we come down the third subtree that gives us 4 possibilities for what min can play, having values 1, 4, 10 and 9. And here's the critical observation. At this point we see a 1. That means that if we're in the third subtree and min is playing, min can force an outcome of a 1. And remember that we want high outcomes for max and low outcomes for min. Now this means that without looking at the rest of the third subtree, or in particular the leaves in the rest of the third subtree, we can immediately stop the Minimax process and backtrack and deal with the fourth subtree. We won't miss any possibilities, and the reason for that is that we've established, when we see that leaf labelled 1, that if the game ever comes to min's turn in the third subtree, min can force an outcome of 1, and low numbers are bad for max. But having said that, we've seen enough of the tree when we've looked at subtrees 1 and 2 to learn that max, as an opening move for the game, already knows how to force an outcome of 6, which is better than 1. So if max is playing rationally, max will never come to the third subtree, and we only need to see that single leaf labelled as a 1 to establish this. Hence the leaves labelled 4, 10 and 9 have been crossed out, because we can't gain anything by looking at those leaves. I'm going to explain that again, because it's kind of critical. If we're doing depth first search left to right, then at the point where we've established that min can force scores of 2 and 6 for the first 2 subtrees, meaning that max can choose to have an outcome of 6 by choosing the second subtree, that means that when we're going left to right depth first and we see a leaf labelled 1 in the third subtree, that tells us that min at that point could force an outcome of a 1, because min is trying to force small outcomes. That means that in the third subtree we don't have to look at any of the other leaves, because we know that max will never come to that subtree, because we already know that if max comes to that subtree, min can force an outcome of 1 or less. So if max is playing rationally, max will go to the second subtree where max can force a 6. So for this really simple game, that's quite straightforward, but now what we want to do is see how this works in general. Now what I have here is an illustration of how the depth first left to right search might work out. Because we're going depth first, we only have direct knowledge of nodes that are in our current path down the game tree. So initially here I have a node, the upward triangle at the top of this diagram, representing a play for the player who is trying to maximize the outcome score. And we're going to assume that we've established at that point in the search through the game tree that if the player gets to that node, they can force a score of at least m. And we'll know that because we'll have looked at some game trees on the left and established that one of them allows max to force an outcome of m. Now we keep a parameter called alpha that we update as we do the search that keeps track of the best score that max can force, given what we know from the information that we've got thus far in the search. Now once we've got a bit further down the current path in the search tree, we may hit another node for max, and after that we'll be looking at nodes for min, who's trying to minimize the outcome score. So we continue our depth first search and we get down to a deeper node for max. And under that, we search left to right in its subtrees, and we establish that min can force an outcome of m prime, and that tells us that the lower of the max nodes here has a value that's at least m prime. So now we know about two of max's nodes. The higher one, where we've established that max can force a value of at least m, and the lower one, where we've established that max can force a value of at least m prime. Now we get down to the node for min at the bottom right. Now, while we're searching under there, we're going to establish that min can force particular values should the game ever reach this point. The key observation is that if we establish that min at the lower right node can force a score of n, which is less than m, then we can stop, we can prune. Okay? Because we will never come down this way. We know that at the top node for max, max could force an outcome of m, which is better than the one that min can force further down the tree. And similarly, if n is less than m prime, we can stop. Because we already know that the lower of these two max nodes can force an outcome greater than or equal to m prime. And so if n is less than that, we're just not going to come down to that part of the search tree. Now all of this I've so far explained in terms of max's play, but of course there is an exactly analogous argument for min's play. It's just that max is trying to maximize and min is trying to minimize the outcome. So in fact we keep the parameter alpha, which is the highest thing that we've seen so far on the path that max can force, and we also keep track of beta, which is the lowest thing we've seen so far on the path that min can force. And those are initialized to -infinity and +infinity respectively. And having worked through that argument, it's fairly easy to write down the code for how Minimax with alpha beta pruning works in general. We start off assuming that it's player, max, who is the first person to play, with the default values for alpha and beta. We're starting from the root of the game. Now, in general, we could be starting from any position in the game. That doesn't really make too much difference. The function looks like this. If we've reached the point at which the cutoff test applies for the node that we're looking at, we just evaluate it and return the evaluation. Now we want a variable called value, which is initialized at -infinity, because what we're trying to do in playing for this maximizing node is keep track of the best outcome that we can force at this node. So then for each successor of our current node, which will be a position where it's the opponent's turn to play, we allow the opponent to play from that position, and that will give us back a value that can be forced by the opponent. And then we keep track of the maximum of our running tally for this value, and the value that we've just established that the opponent can force. Now, here is the key line where the pruning takes place. If the value is greater than beta, then we return the value. Why is that? Well, we are keeping the maximum value that we know we can force at this point in the search. If that value is greater than beta, well, let's remind ourselves of what beta denotes. Beta is the smallest value that we've established that the opponent can force at some point along the current path through our search. That means we already know that at some point in the current path in the search, the opponent can force a value of beta. And because the value that we've established that the maximizing node, the player's node, can force right here is greater than that, we know that we'll never get to this point in the search because the opponent can do something better at an earlier point. Now the final thing here is that we are of course also keeping track of alpha for the player, which is the best thing we know that the player can force. If the value that we've now established is greater than alpha, then alpha needs to be updated. So that's the final part in the third if statement. And finally, having gone through each successor and found the maximum value that the player can force through all of its subtrees, we return that value. And unsurprisingly, the function for the opponent is exactly analogous. Okay? Once again, we have running values for alpha and beta. We're at a particular node within the game tree. If it's a point at which we can establish that we're going to do a cutoff, then we just evaluate the position we're at and return the result. Otherwise, now we're playing the opponent who is minimizing. So our value keeps track of the smallest outcome that the player can force in a subtree of node n. So we allow the player to play for each of the successor positions, n prime. We keep track of the smallest value that can be forced, because now we're the opponent and we're minimizing. If that value is less than alpha, we do the pruning. We just return the value, okay? Because alpha is the value that we already know that the player who is maximizing can force, given what we know about the current path through the search tree. So if here the opponent has established that it can force a value that's less than that, we just know that we won't get to this point in the search. And finally, beta is keeping track of the smallest value that we know we can force. So if we've now arrived at a value that is less than the current value for beta, we can update beta. Now if you apply this and keep track of what's going on to the earlier simple example, this is what you should find. And I leave that to you as a further problem, a further exercise, just to get this fixed in your head so you understand what's going on. Now, in exactly the same way as I did for the earlier material on the intelligence search, I'm just going to point out some theory-oriented results about the effectiveness of alpha-beta pruning. Now, if you think about this game playing process a bit, you should be able to establish to your own satisfaction that the order in which you try moves makes a difference to how alpha-beta will end up pruning things. Because if you try good moves, you're more likely to force a good outcome than if you try bad moves first. Now, it turns out that if you had a perfect move ordering technique, then alpha-beta pruning would result in a search process that's order q to the p over 2, as opposed to order q to the p. So that means you'd expect to be able to search twice as many moves as before, for a given limit on time. Now that's clearly not realistic, because if you had a perfect way of ordering your moves, you'd be able to play perfect games. So, can we do anything a bit more realistic? Well, it turns out that if you arrange your moves at random, then for a sufficiently large queue, you can get order q over log q all to the power of p, which is better than order q to the p. Or for reasonable values of q, you can get order q to the 3/4 p. So, something in between nothing and perfect move ordering. Now in practice, it turns out that employing just simple move ordering techniques can be a pretty good strategy. So in chess, you might want to try moves that are in some sense intuitively good ones first. So capturing a piece from the other side, or moving a piece to where it's attacking the opponent's king, or moving pawns forward, and so on, might be things that you want to try before apparently less effective moves. And another approach you can take is that you try something like iterative deepening, but you run a search for your next move. Now, in doing this, you'll get some information about how good possible moves in the near future of the game are, and you can use those to order your moves for the search at the next step. Okay, so it's yet another variation on iterative deepening in order to try and make this more effective. Now, the final thing that I need to point out about this kind of game playing is that, of course, I've explained everything in terms of trees, whereas in fact we're doing game playing searching in graphs, which means that you have the same problem as you did before for intelligent search, namely that you might be able to get to a particular position within the game by multiple different routes. Now, that's then addressed using exactly the same idea as for intelligent search. You store a state with its evaluation in a hash table. That's generally in the game playing literature called a transposition table, and you do this the first time that your state is seen. Now, that's essentially the same thing as a close list, and it can increase the effectiveness in precisely the same way.